Hello, welcome to my channel. Welcome to Practical Electronics 5. In this practical, we're going to be dealing with real-life application of PWM, pulse width modulation, how to power your laptop, your music keyboard, and other DC appliances from solar panel. So what you are seeing here, this is a buck boost converter that you are seeing here. So if you remember our previous practical, we treated this. I showed you the circuit board that I constructed, which we were able to also to charge our phone from the solar panel. And I showed you this. I made mention I'm going to construct this, so which is what you are seeing here, the diagram, the circuit diagram, and this is the constructed device that you are seeing here. So this is a buck boost converter. So before we go further, let's flash back what we covered previously. That's on our practical electronics 4. That was our previous practical. We did this, and then we talked about types of DC power supply, where we talked about linear mode power supply, which I did, which is what you are seeing here. This linear mode power supply, that's a regulated DC power supply whereby the input is higher than the output. And then we also covered switch mode, so which is what we are going to be dealing with, switch mode power supply. So in this practical electronics 5, PWM pulse. What is this PWM about? This system is what our phone charger, laptop charger, many other power supplies, your solar charge controller, they make use of this system. So we want to see how this thing is applied in real life. So let's take a look at the circuit diagram. So this is a buck boost converter. So this is it, a buck boost converter. So before we go into the explaining how the system works and what it does, so let's take a look at switch mode power supply. An electronic power supply that incorporates a switching regulator to convert electrical power efficiently using digital signals as PWM. So what you are seeing here is PWM. PWM, these are the signals. Look at how they are. The signals come out from here and control this and the rest of this, which I'm going to explain. So let's come down. In this, we are going to look at buck converter. So what is buck converter? Or you can also call it step-down converter. Buck converter or step-down converter. Now the name step-down. A DC to DC converter which decreases voltage while increasing current from its input, that's the supply, to its output, that's the output. Your laptop charger, phone charger, keyboard adapter, TVs, etc. uses a buck converter. So how does it was just like what we are seeing here. Buck converted means the input voltage will be higher than the output voltage. Buck step down converter, so which means we are using some sort of signals to step down the high voltage to a low voltage DC. So any device that does that, we call that device buck converter or step down converter. Your phone power bank uses this type of converter. Now your power, both those of you who have used power bank for mobile phones, your power bank when you plug in your USB charger to your power bank, the buck converter will be activated. So the battery in your power bank is 3.7 volts. Then the USB voltage is 5 volts. So the buck converter needs to scale down the voltage, chop down the voltage to match that of the battery. So you see, so that's buck converter. The same thing, your charger of your laptop. After the rectifier, where we have the DC, that's after the AC has been converted to DC, which is around 300 and something volts. Then, and you know your laptop needs 18 volts. So it is the job of the buck converter to bring down that 380 volts down to 18 volts, which goes to your laptop. The same thing with your phone, with many other modern electronics gadget that operate from AC or from any other high voltage DC. So let's take a look at this again. Boost converter. Boost, step up. You know, the other one, the opposite of the other one, a buck, step down. Why this other one is the boost, step up? It means that you are making something to go higher, up, increasing. So let's take a look at this. A DC to DC converter that increases voltage while decreasing current from its input supply to its output. So this one will, for example, let's say you have 12 volts and you need 18 volts to run your laptop. So the boost converter will convert the DC voltage into AC oscillating voltage and then reconvert it back to DC at the 18 volts. So which means the input voltage is lower than the output voltage. So devices which does that is a boost converter. Now this boost converter is also inside your power bank. Your phone power bank uses a boost converter to convert 3.7 volt DC to 5 volt to charge your phone. So you see, so two of these converters are in the power bank of your phone, buck converter and boost converter. That when you want to make use of the phone, your phone battery is low, so you need a power bank. When you plug your USB cable to the power bank, the boost converter will boost the voltage because the 3.7 volts won't be able to charge your phone. So it will boost this 3.7 volts to 5 volts so that it will charge your phone. So let's take a look at the third one, buck boost. So you are seeing buck boost. It means there are two things involved: a step down converter and a step up converter. So you see, so this is a type of DC to DC converter that has an output voltage magnitude that is either greater than or less than the input voltage magnitude. The output voltage can be fixed or adjustable. So you see, so which is what we are going to be looking at, this particular one, buck boost, which is what I've constructed. So I've shown you this before. This is a buck boost converter. I ordered this one from AliExpress. So you see, this is the input voltage. I can put in 12 volts here and get 18 volts, or even get even 5 volts, or even 25 volts, because the output is adjustable. This potentiometer you can see is adjustable. So you see, so down to the one we have constructed. This is my input and this is my output. So you see, so let's finally talk about this PWM. Most of us will be hearing this. Pulse width modulation. A rectangular wave with a variable duty cycle. A technique used to control analog signal using digital signal. So they are just like this. So when you're talking about these are pulses, something that come on and off, on and off, on and off. So this on, off, on, off. So when you're talking about pulse width, it means the wideness. The time this pulse was on, how long does it stay? And when the pulse goes off, it's just like a voltage come on, stays for a particular time, then the voltage goes up. So the duty cycle we are referring to here is just the ratio of this, the on time to the off time. So you see, so this is how the signals are. So this is just what I'll be we'll be dealing with this in our subsequent tutorial when we'll be doing uh, using PWM to control devices. We're going to be dealing with this very so for this sake of our practical. So let's come back to our circuit diagram. So before I explain this, I'm going to connect this device to a DC source. Your DC source could be solar panels, it could be from batteries. For example, now you have your laptop. You know your laptop needs 18 volts. Your laptop needs 18 volts. And then you have a 12-volt battery or 12-volt solar panel. This goes to the solar panel or the 12-volt battery. Then this is the output. So let me connect this up so that we see how it works. So I'm going to connect this to my DC source from my solar panel to the negative and the positive. Then I'm going to hook up my meter so that you can see the voltage, the input voltage. So here is our digital meter. So I'll fade in the power source, that's our input voltage. So this is so you can see my output voltage. This is the output voltage. You can see this meter is connected to the output, then this one is connected to the input. So you see, so on the device here, what you are seeing here is I can adjust the output voltage. So let's say we want to power our laptop with this. You know, this voltage is too high. You can see 28. So I'm going to adjust this. You just have to just adjust it gradually so that so we need 18 volts. So I will just set it at 18 volts. Bring it down a little. So you can see input voltage. You can even see the input voltage 11.7 volt, but you can see the output voltage. You can see the output 18.3 volts. So this is boost. So it's working in the boost converter now is working. So you see, so the boost converter is working. Okay, what if I need something like 5 volts? So which means I want the buck converter to work. So you can see this is the buck converter now at work. So I want 5 volts. Now before you connect such kind of thing to a load, make sure you adjust the voltage first. Don't connect it to a load while adjusting the voltage. You could cause some damage. So before you connect this into a device, adjust this to the rated voltage of that device before you connect it. So let's this is 5 points. Let's leave it as 5.2 or 5 points. So let's leave it at this. So you can see. So this particular one, you can even charge your phone with this. If you have your USB, you can wire to this output. So you see, so this is 5 volt, which means you can power 5-volt device. So you can look at the input voltage higher than the output voltage. So we have understood how a buck boost converter works. So you see, so we have understood how a buck boost converter works. So let's turn it off so that I will explain all we go to the explanation of how it works. Let's disconnect everything. So let's go to the circuit diagram. So if you look at our circuit diagram, this is our diode. Look at the diode there. You can see the diode. This is our fuse. We have our capacitors, reservoir capacitors, and the other one filter capacitors for noise. Then we also have a LED indicator on the input side. So look at the capacitor here. Then the non-polarized capacitor, you can look at the indicator, LED, and the resistor on it there. So what we have here, this is a transformer. This is a high frequency transformer. It's different from the conventional transformer we know, the low frequency iron core heavy transformer. This is high frequency transformer. This type of transformer, it operates at high frequency. So you can see, so there are two windings here. This is the primary winding, this is the secondary winding. So this is the transformer, and if you look at it here, this is the transformer that you're seeing here. So this is our primary winding, and then here we have our secondary winding. You can see it here. So this ring you are seeing here, this is a ferrite core. I got this from a condemned power pack, computer power pack. You can remove this ring from them. So that's where I got this. So you see, so that's what you are seeing in the diagram. Now let's go back to the circuit. If you look at here, there is a capacitor here also that connects the primary winding to the secondary winding. This is the capacitor you are seeing here. Then if you go further, this is high speed diode that you are seeing here, high speed diode. No, you can't use the ordinary diode here. Here I use a 6A1 diode here because I ordered at the time I was building this. I didn't have the diode, so I just use. Although I've ordered for diode, which I'm going to replace them. Even this one you are seeing here, I didn't get exactly of this diode. So you can, if you look at it here, I also removed this from computer power pack. So you see, so this is not the diode I'm supposed to use here, but I'm going to replace it. I just make sure I want to test that everything is working. So there's a diode. This looks like transistor, but it's not a transistor, it's a diode. So you see the high speed diode. So, and then we still have our output capacitors here. We also have our output indicator that you see here. The output capacitor, what you are seeing here. Then we also have indicator LED here. You can see it. So let's come down this side again, where we have this system here. It what generates the PWM signals, the signals that are needed. So you see, so it has there are two inputs here. One of the inputs, we call it feedback, voltage feedback. You can see from the output voltage, it goes back to the input through a potentiometer. This potentiometer that you're seeing here is for adjusting the output, because the system here need to know the output voltage so that it can compare it to a reference point. You can compare it to a reference point. So this pin 8 is a reference voltage. That's about 5 volts, which the chip uses. So it will be comparing this with the output voltage so that it can adjust the PWM going out. So the IC I use here is UC3843. So it's a switch mode power supply IC. So you see, so the second input is the current input. The load overloading now, the load is drawing out current from it. The IC can be able to sense it from here, so that if the current goes high, in order not to damage this in the IC can make the way to like adjust the PWM to reduce the output. So in order not to cause damage. So this is the current feedback. Why is so down the voltage feedback? So this IC you are seeing here, pin 5 goes to ground. Pin 5 is the negative terminal of the power supply, while pin 7 is the positive. So if you look at it here, that you're seeing here, so this is the IC here, this is the input. You can see through a resistor. So the input, you are seeing it through a resistor. If you like, can you add diode, but diode is not too necessary because I already have diode here. But anyway, you can still go. Then make sure you have some resistor like 4 points, between 4 ohms to 10 ohms resistor. Just put it. So then this pin 6 here is the PWM output. Pin 8 is the reference voltage, that's 5 volt reference voltage. You can see here. Then pin 8 is the reference voltage. Make sure you have a filter capacitor at this point. Then pin 4 that you're seeing here is the pin that sets the frequency. Although I have not measured the frequency of this because I have not measured the frequency of this particular thing because I don't have that high speed oscilloscope. So if you have a high speed oscilloscope, after building this, after testing it, confirming working, you can measure the frequency. So this is where you measure. If you want to measure the frequency of this circuit, this is where you measure the frequency. Here, this pin 6, you can measure the frequency to know how many kilohertz this is running at. So this capacitor and this resistor here set up the frequency. So you can see the resistors here with the capacitor. So the set up, although I didn't have the exact value here, so you can see them, I didn't have the exact value there, so I used something close to it there and it's still working. So these two resistors and this capacitor sets up the frequency at which the PWM is generated. So pin 3 is the current feedback. If you look at it, this is the MOSFET. Where is the MOSFET here? Look at the MOSFET here. I use an IRF 2907. So this is the exact MOSFET I used. You understand? So you can use any MOSFET you wish depending on your requirement. Then your MOSFET, make sure you have. Now at the time of designing this, I don't have that value of resistor. So this is what I did. I didn't have this value of resistor at the time I was designing the circuit. So if you look what on the circuit, there is 0.05 ohms. So I didn't have that value. So what did I do? So if you look at this resistor, there are 4 resistors I put in parallel. So that's 0. This resistors here. What I did, this calculation we do in school there, resistors in series, resistors in parallel. In real life situation where we need to apply such things. So what I did was I put 4 of them, 0.22 divided by 4, which gave me 0. So you can see 0.055. So if you look at what's our requirement, 0.05. So you can see it's almost what we need there. So how I did it. So because this resistor available in the market, so I bought them and put them 4 in parallel. So you see, now take note of this. In school, you see electronics engineering students, they can solve equations very well, pass the exam, get good grades. But when they go out in real life, they cannot be able to apply those calculations that they are doing it, which is not good, which is not a good thing. So you see, just resistors in parallel that we do in the class to pass exams, which apply to solve a real life problem here. You are seeing here, you can see it. So, and what was the problem here? I don't have this value. I couldn't get access to this value of resistor in the market, and I found out which of them they have, and I had to make a calculation which give me almost exactly what I needed. You see, so you can see. So whatever you be reading theoretical, please make sure you try it, apply it in real life, because that's the essence of why we go to school. The essence of why we go to school. So if you go to school and solve equations and in real life problem encounter such kind of challenge like this and you don't even know what to do. Some of you just busy carrying any other value of resistor and just without checking the value. For example, now someone maybe will go and be carrying 220 ohms because that was what he could see in the market. He just bought it and he just buy it and just connecting it. This is going to not give you what you want. It will make this into misbehave and not give you exactly what you want. So we want to make things right. You understand? Your electronics is not just a guesswork. You need to be precise in whatever you're doing. So you can see. So that was how I was able to get this value of resistors and it's working exactly the way I designed it and working. So you can see. So then make sure you also connect this also. Now, why is this resistor there? In case something bad happens here. Now, if you are still going to be, if I'm still going to be designing this again, I'm still going to put a Zener diode here. I'm still going to connect the Zener diode here, like for example, 5 volt Zener diode. So in case something happens here, you don't go and blow this IC. Because if this place is disconnected, the whole voltage that's supposed to go ground, it will go and pass, like try to pass through the IC to ground. You can blow this IC up so you can see. So make sure the resistor have to be there first so that before you can put your Zener diode. Although I didn't put the Zener diode. So here is the PWM output. So this is your MOSFET. If you look at the circuit very well, the primary winding, the beginning of the coil, we have the beginning of the coil, the ending of the coil. You see these dots? Usually, if you see this dot in the circuit, we are usually referring to this type of, if you see the diagram here, with those dots, you are referring to those kind of transformer winding, this type of transformer. So this is the beginning of the first coil, the ending of the first coil, the beginning of the second coil, the ending of the second coil. So you see these dots indicate their directions. So the beginning goes to the input, as you can see it here, the beginning of the transformer now. Why is this fuse here? In case there's short circuit at the output, when anything bad happens, you don't burn some other thing, the fuse just cut immediately. So you see, so take note of that. So the beginning coil goes to the input, the ending of the coil. What connects to this is the drain. Now this, remember this type of transistor, this MOSFET, metal oxide semiconductor field effect transistor. So this is gate, this is drain, this is source. So take note of that. Now inside this transistor, we know that there's a diode here. So you see. So let me explain why I put this diode here. Mistakenly, if you reverse this input, let's say you mistakenly connect this to a negative terminal and you connect to a power source and you connect the negative to a positive, current to flow and you're going to burn this, blow this transistor up. You understand? You're going to blow this transistor up. So to prevent that, I put input at this diode. Even this other one I ordered from AliExpress, you can see I put protective diode. So in case I reverse the input voltage, is to protect the system here. So you can see, so that's the reason why I put that diode there. So let's look at it. So the first coil, the starting of the first coil goes to the positive terminal of the input, while the ending of the first coil goes to the drain terminal of your MOSFET. Now the second coil, the beginning of the second coil goes to ground, it's connected to ground, while the ending of the second coil is the actual output. Now you can't connect this into this, you can't get DC here at this point. You're having alternating, the voltage is pulsating. We call this pulsating DC, on and off, on and off. So it's a pulsating DC we have here. So we need pure DC. You understand? We need pure DC. So here we have pulsating DC. So how do we, and the pulsating DC operator running at the frequency of this PWM. So it's at that frequency, very high frequency. So what do we need? That's why we need high speed diode. You can't just connect a normal rectifier diode here, no. The high speed diode. So these are diodes that work with high frequency. So that's why we have this type of diode here. Called Schottky diode. So you can see the symbol here. So we have two of them here, diode, which is what you are seeing here. You can see the diode there. So then after the diode there, you need capacitors. It's just like if you are converting AC to DC here. What you have here is just the behavior of AC volt alternating voltage. That's just the behavior you are having at this point here. It is oscillating DC voltage. So you can see, so it is not a pure DC. So you see, so that's why we need this high-speed diode, so that it will convert it back to pure DC. And then we have the capacitors here, also filter capacitors that you are seeing at the output here. So that's how we get the pure DC out. Then we need to tap, you can see this connection, you need to tap this back to the input. Now, how do you get to the input of this? Now, what this feedback is just like the mirrors you have on your car, so that you can be able to know what is going on behind you, so that you can adjust your driving. So this is what's happening. So this potentiometer that you're seeing here, you can see the potentiometer here. If you turn this potentiometer this direction, if you turn this potentiometer down this way, the output voltage is going to increase. If you turn the potentiometer to the other direction, the output voltage is going to drop. So you can see, so this system here, the maximum output voltage is 30 volts. You understand? And then the minimum input voltage, you can adjust it to, it can go down to below 2.7 volts. So you see, then the input voltage, based on this IC here, the input voltage is maximum 30 volts. So that's the range this thing operates. So the input voltage for this thing to be able to regulate properly, around 10 volts. So if I have 10 volts, I can get 30 volts here, or adjust with any voltage within that range. So you see, so this particular one, just I've said that's for current sensing, to sense current, why it's going to sense the output voltage. So that's how the entire system works. So you see, so that's how the entire system works. If you look at the back, if you are constructing this thing, if you look at this, I use very thick copper wires here. That's for the ground terminals. So at this point, you can see the thick copper wires I use. Very thick. Why? Because around this area, you're having high current. So you can see around, so you have high current. So those areas, make sure your connections are very thick, so you can see them. So you can see so this how so with this now, I don't have issue. Oh, I need a 7 volts. I have solar panel that is giving me 24 volts and I need 7 volts, or I have solar panel giving me 30 volts and I just need 7 volts to power something. What do? I just adjust this thing to whichever voltage I want. My meter, I've already connected this to power your device. So set it, so you can see. So the knowledge of electronics, I have put it practically to create something that will solve real life problems. One of the problems we have in this country here in Nigeria, power problem, power supply. The power is not enough for everyone, so we need to figure out ways of powering some of our gadgets. So from your solar panel with this, you don't have issues working on your powering your DC devices. So you see, so this can run from any DC source, whether it's solar panel, whether it's battery, or whether it's from wind, as long as it is DC source with between 10 and 30 volts. You just put in this. So you see, so you guys out there, electronics engineering students, don't depend on the school. The school is not going to give you this skill. You need to develop it yourself. The school won't give you what the school will do. What the school will do, they help you to get your academic qualification. That's what the school will give you. So you need to get access to practical and theoretical textbooks. The kind of textbooks we have in our schools are academic textbook. You can read the whole of an academic textbook in electronics, but you cannot design something like this. You cannot. You can't design something like this. If you like, repeat the book, read it all over and over again. The highest thing that book can do for you is to help you to pass exams. But for you to get the real life knowledge, you need to get access to real life electronics textbook, real life theoretical theoretical textbooks. That's what you need. You need to be able to build things like this. Also go to the internet, read. Those who read in this world are not those who are in school. Those who are putting ideas to solve real life problems, they are the people who are reading. So I don't consider someone in school reading just to pass the exam if that is just the aim of your reading. I don't consider that as reading. If you read to acquire knowledge and in a real life you are putting forth that knowledge and is solving a real life problem, that's where I can now say you are reading. So I have done mine. It's your turn. So let me show you the circuit again so I can take a good look at it. Observe the circuit very well, draw it down and go and try it. Now some of these components, I bought some of them, but some of them I didn't buy them. So that's why it's good to have scrap. Don't be throwing away your condemned electrical gadgets. Don't be throwing them away. So it's all like this one there. I bought the coil, but the ring, I have to remove it from some old boards, circuit boards. And also this is, if you look at this, if you open your laptop charger, you'll be seeing this. So I removed this from an old spoiled laptop charger. So I have to get this to heat sink. Now when you are putting this thing, is very necessary, but this get hot when you've powered some, when you connected load here. So the more current the load is drawing. So this system here can operate. Now your input need to be like 10 amps, 10 amps and above. So your input should be 10 amps and above. So take note of that. So this heat sink is very necessary. This one gets hot, so that's why you must put some aluminum uh, heat sink. So this is an heat sink I put here, so you can see. So and if this thing is going to be running for longer hours and you are drawing much current, cooling fan is also necessary. You understand? So I've used this to charge batteries, like lithium-ion batteries. You can use this to test a lot of in my workshop. So try and build mix. So take it as an assignment upon yourself. Go and try and make something. So we be ending this tutorial video. So if you like this video, share it, like it, subscribe to my channel. Thank you.